Tesla Cult here, and this is a computer program for taking readings on a magnetometer. And what I use this for is for watching changes in the geomagnetic field. This is the magnetometer right here. You can see the sensor on top, and then I have a real-time readout display on the front here. And this is basically what I'm going to be covering today. I'm going to show you how to build this. And this program I'm not going to cover today, but I'll give you a description of what it does here. But it basically records the data coming from the sensor and processes it as well. You can see up here in the upper left corner the three top numbers, X, Y, Z. That's the incoming data. And then I do a quick little process. This is just troubleshooting information so I can ensure that the program's functioning properly while I'm working on it, and when I start it up. I now have dates and times on the x-axis of the graph. I just got that done, and I'm adding a drop-down bar here for changing time zones. And this is start and end times and dates here. I'll probably be removing some of this as I go, but for now, they serve a functional purpose to me. This top reading here is your H field, or total field strength. It takes the incoming data and uses a variation, a three-dimensional variation on the Pythagorean theorem, by taking the square root of x squared plus y squared plus z squared, and that gives me a total field strength. There's some other processing that goes on there too, because I gotta convert the variables to nanoteslas. I'll discuss that a bit later on. This is your horizontal angle. This is kind of like your standard compass reading, except this is just for measuring changes in that reading. And this uses this is your D measurement. These are standardized in this field of I guess this would be geology or something like that. But anyway, arctangent y-axis over x-axis, and this gives me the horizontal angle. And down here, this one isn't always included, but this is your vertical angle, which is arctangent x-axis over y-axis. And it records the readings there. Now, the way this program works is that it actually, the data is received once a second, as you can see here, and it takes this data and sums it over the course of a minute, and then averages out the readings, and then the graph is updated once a minute with the information. So anyway, let me show you the schematic here. And this is the schematic. You have the LCD screen and the wire buses that lead to the microcontroller and the magnetometer. These are the parts right here. This is the microcontroller, and I think it's an Arduino Mini or something like that. And then this is the LCD screen. And this, what is it? QC1602A. And the magnetometer, which is a GY271. But anyhow, most of the wiring for the LCD screen is defined in the program, so don't worry too much about tracing the wires right now, because you can get most of that. You know, you have the power, and this little potentiometer up here is for adjusting the contrast on the LCD screen. I omitted it myself. I just set it for maximum contrast. But the wiring for the magnetometer is not defined in the program. It's defined in the library class. So that what you need to know here, because you have the power and the ground, of course, but A5 goes to your SCL pin, and A4 goes to your SDA pin. Or at least I'm pretty certain that's what it is. I don't think I screwed it up. I don't think I got it backwards, but that should be it. Anyhow, let's move on here and let's call up the program. And this is the program for running the microcontroller. This isn't the program for doing the screen graphing and all that. But this will get the magnetometer, the microcontroller and magnetometer running. It's kind of like a digital compass. It's actually a very sensitive compass. It's pretty accurate, actually. I mean, you can measure with just like tenths of a degree here. You know, I mean, those fluctuations you see are actually the movement of the magnetic field that you wouldn't normally see with a regular compass, you know. But anyhow, let's go back to the program here. We got £, include, bracket, wire.h, close bracket. That's your your library for doing the serial communications. You got £, include, bracket, QMC 5883L, compass.h, and that's your library for the compass, or the magnetometer rather. And £, include, bracket, liquid crystal.h, close bracket. That's your library for the LCD screen. You've got £, include, bracket, math.h, close bracket, and that's a library for doing math operations. Here we're going to initialize classes and variables. QMC 5883L compass. We'll create an instance compass named compass here, and we have constant integers rs equals 2, comma en equals 3, d4 equals 4, d5 equals 5, d6 equals 6, and d7 equals 7. These are your pinouts for the LCD screen, and those variables plug right in here. Liquid crystal, create an instance LCD, RS, EN, D4, D5, D6, and D7. So those variables plug right into there. I just basically did it that way to be orderly, so that anyway, integers X, Y, and Z, which is fine because the data comes off as integers, so there's no need for anything more. Now here I use double X local equals 0, Y local equals 0, and Z local equals 0. Now these are the variables for the LCD readout. In the double, H equals 0, I equals 0, and D equals 0. And the same thing is for the LCD readout, because the data is sent to the computer in its raw XYZ format. So this is just processing to this is just for the processing to create the readout on the LCD. So void setup, wire dot begin, open and close brackets, serial dot begin, bracket 9600 close bracket. That's your baud rate. Now the wire begin, that starts your serial communications begin. Compass dot initialize, open and close brackets, and LCD dot begin bracket 16,2. Now this basically defines the size of the LCD screen. And then that's your setup. And here we have the start of the program, basically. Void loop, or the loop that basically runs the functionality of it. Compass dot read, open and close brackets, that reads the magnetometer. X equals compass dot get X, open and close brackets, that reads your defines X as your X reading. If X equals 0, X local equals 0, else X local equals X divided by 100. And the reason for that little routine there is because the math register on the microcontroller is only so big, so I had to cut the size of the numbers down to make it fit. It cuts down on the accuracy a little bit, but I don't have to do that on the computer program, so it doesn't really matter. Y equals compass dot get Y, open and close brackets. If Y is equal to 0, Y local is equal to 0, else Y local equals Y divided by 100. And let's see here. Z equals compass dot get Z, brackets. If Z is equal to 0, Z local equals 0, else Z local is equal to Z divided by 100. And then here's where I process the information for the LCD readout. We got H equals square root of X local times X local plus Y local plus Y local plus Z local plus Z local times 1200. Now if you're wondering why I spelled it out like that, it just wasn't worth the trouble of using the routines for the square, so I just typed it out like that. And the multiplier here times 1200 is for a couple of reasons. Number one, the information coming off the magnetometer has to be converted to a standardized system like Gauss or Tesla's, and the readings are in nanotesla, so the times 1200 basically does that conversion, to the best is what I can figure. Anyway, D equals A tan 2 minus X comma Y times 180 divided by 3.14. Now the reason for the 180 divided by 3.4, now obviously the tangent of XY gives you an angle, but the angle's in radians. So the 180 divided by a 3.14 converts it to degrees. If D is less than or equal to 0, D equals 360 plus D. Now the reason for that is because the information is basically when it's converted to degrees, it's 0 to positive 180 degrees or 0 to negative 180 degrees. So this does a conversion to 360 degrees. Same thing here. I is equal to arctangent 2 negative Z comma negative Y times 180 divided by 3.14. If I is less than or equal to 0, I equals 360 plus I. And then here is The LCD output, I start by clearing the screen. LCD set cursor 0, 0. LCD print quote D apostrophe close quote. LCD print D, 1. And LCD write 2, 2, 3. And then again, let me explain this. You set the cursor 0, 0. This is the upper left corner. Print quotation D apostrophe. That basically prints the D here. This is to create this screen right here. You see a D apostrophe, and then you see the readout in degrees with the little degree symbol there. That's true for the D, the I, and then the H down here is given in nanoteslas. So that's what this is creating right here. So this one, the second one, LCD set cursor 0, 1, sets the second line. LCD print H quote H apostrophe close quote. LCD print H, 0. LCD print quotation nanoteslas. And then down here we got LCD set cursor 8, 0. LCD print quote I apostrophe close quote. LCD print I, 1. LCD write 2, 2, 3. Serial data output. So this is the information being sent to the computer. Serial print line X, serial print line Y, serial print line Z. And delay 1000 creates the 1 second delay on the microcontroller. And then the data is cleared. Everything's equal to 0, and it's the end of the loop. So that's the program for the microcontroller. And I will probably do a video on this program later on when it's closer to being done. But it's pretty extensive even now, even though it's not even finished. But anyway, I hope that helps recreate the magnetometer if you like. And Tesla Colt signing out.